Today's lesson is all about reviewing those exponent rules so that we can be more proficient dealing with logarithms. Because as we talked about yesterday in the video, logarithm is an exponent. When we are dealing with logarithms, we have to know exponent rules like they're the back of our hand. We cannot separate them because they are really one and the same. A logarithm is an exponent. So when we're doing today's lesson, don't just be thinking about exponents and why are we doing these exponents, but instead think, how is this going to link to logarithms? Because that's where we're headed with this. And so today is all about those exponential rules, in particular how we handle exponents to simply multiply or divide, and then again how we can look at fractional exponents and what do those mean as well. Eventually we'll be applying those to logs. So all right, with that in mind, looking at this first question, 128 times 4,096, obviously we could, off to the side of our paper, multiply 4,096, or we could use our calculator, but since that's not an option for this class, like what you wish, we want to approach this using exponents. So hopefully you have your two chart relatively close by, and I want you to look and see what is 128. Looking at that chart, that's 2 to the 7th. 4,096 is 2 to the, great. Now, what do we do with our exponents when we are multiplying? We add them. And so I'd get 2 to the 19th, and so there I would get 524,288. Beautiful. Certainly much faster than multiplying those two numbers together. Let's look at the next one. How about 65,536? Well, that's 2 to the 16th. Divided by this next number here that you see, 1,048,576, which is 2 to the 20th. Certainly, I don't want to deal with those decimals in that multiplication. This is far easier to simply say, oh, well, that's 2 to the negative 4, so that's 1 over 16. You certainly can't argue with that. Now 64 to the 4th. Again, we could do 64 times 64 times 64 times 64. Or we could look at the possibility of saying, hey, that's the same thing as 2 to the 6th raised to the 4th, so that's 2 to the 24th. And then look quickly at the chart and say, oh, that's 16,777,216. Amazing how much faster that is than multiplying. And you can see why the discovery of exponents really lightened the load for these mathematicians. Now let's look at logs. Again, keeping this in mind, and then we're going to move to the fractional exponents today. What does the log mean? A log is an exponent. I want to keep that close to your mind. So really this first question is saying 2 to what power is 524,288? Looking at your chart, you should get 19. All right. 3 to what power is 3? Wonderful. All right. Here's one that tends to trip people up. 4 to what power is 1? Anything to the 0 power is 1. And so it didn't matter what that base was. If I wanted 1, I could automatically say, hey, that's 0. All right. If you were looking at this with my hand in front of you, I would basically be covering up the 1 in that slash and say, okay, how do I get 5 to be 25? And hopefully you quickly say that's 2. So then how do I flip it? Very good, negative. In the same way, it looks a little confusing here because the base is a fraction. We're not used to seeing that. But the truth is it's the same approach. We understand that 10 to the first power would be 10, so it really doesn't alter that 10 at all, except that it does flip it. It makes it from 1/10 to 10, and so that simply could be done just by putting a negative in front of that. All right, now in the last part of this video, as I told you before, is what I want to work on are these fractional exponents. Eventually we will be linking these two logs, and you'll see how they actually all kind of go together here. So let's just do this question. Before we get into all of these examples, I want us to first recall from last year, what do each of these parts mean? The P represents the exponent, or the power. Again, that's the exponent, or the power. the number here, or in this case it's a letter, but the number that's representing is the root, or the square root, the cube root, the fourth root. And x, sometimes will be an x, but sometimes it'll even be a number. So if I was to write this out, this really means the cube root of x to the p. Another way that this could be written is the cube root of x, and then we raise it to the power. And I will tell you that this is the most common. The reason it's the most common, because without the calculator, it brings the number to a smaller level, and then you raise it to a power. So in this first case here, obviously if I was to raise 8 to the first power first, that doesn't change it at all. And then you would do the cube root of 8. You'll see what I mean here in a moment in terms of the order of which we do that. But the cube root of 8 is 2, and then 2 to the first power is 2. What I really want to encourage you is to do it in that form. In fact, that I would do the cube root of 8, and then I would square it, rather than looking at 8 squared and saying, oh, that's 64, and trying to do the cube root of 64. Do you see the difference? Because the cube root of 64, although many of you might know that answer, when you think about that, it's not as quick as if I said the cube root of 8, you'd go, oh, 2, and then 2 squared is 4. No problem. Similarly, this next one, 16 cubed. You don't know what that is. In fact, many of you would have to go 16 times 16 times 16. All right, but what if instead I said, how about you do the square root of 16, and then you cube that? So instead what you're dealing with is 4 cubed. And you might think, well, I don't know that as well, but you do know 4 squared. And then you could do 16 times 4, and regardless, you get 64. And if that's not as simple enough, truth be told, using what we just did in the previous part of this, you could have rewritten that 4 to be 2 squared and say, hey, I'm going to multiply those exponents because I'm raising it to a power, and say, oh, that's the same thing as 2 to the 6th. Looking at your 2 chart, what do you know? It's 64. Whichever way you discover that answer, feel free. Okay, again, whether you flip this first or you do the cube root or you raise it to the power, that part doesn't matter. Truth be told, I save the flipping to the last unless I'm dealing with a fraction one. And I'll show you what I mean when we get to the last 2 examples here. So really when I look at this, I say, okay, I'm going to do the cube root of 8, and then I'm going to flip that. So that would be 1/2. Looking at these ones here to the right, again, I would do the 4th root of 16. Then I would raise that to the -3 power. Well, the 4th root, of course, is 2, and to the -3 power would be 1/8. Okay, this is what I was talking about. See how that negative is there? So I might, again, it really doesn't matter. That's the beautiful part about math, that there's many different approaches. And then I would do the square root of it. Keep in mind that that one's not going to affect it, but the square root basically says I'm going to do the square root of the top and the square root of the bottom. Again, another approach could have been to do the square root first. And so instead having the square root of 9/25 and then flipping it. And either way, it doesn't matter because the square root of 9 is 3 and the square root of 25 is 5. And guess what happens when you flip it? Sure enough, you get 5. So it doesn't matter as you're doing this. Now, there's just one more extended thing that I want to look at, is how does this work when solving equations? Because that's really the bottom line in dealing with logarithms. See, the logs were used because they needed to give a value to things that they couldn't figure out what power it was. And although these 3 examples don't illustrate that, what would you say if I said, I want to know what power it would be? 3 to what power is 5? And so that was the whole point of using logs. We needed some way of expressing. We know there's a number. We know there's a value for that, but what do we use? And we'll get into that more graphically, actually, as the chapter progresses. But let's look at this one. This is saying 3 to what power is 81? Now, in using logs, we could simply write it like this. Log equals the exponent, right? So that would mean that I'd have x equals, meaning that's the power. That's what that's expressing. And so I would say, okay, log, what's the base of that power? Well, that's 3, is 81. Now, I don't really want you to leave it like that. I actually want you to answer this question. 3 to what power is 81? And of course, the answer to that is 4. 3 to the 4th is 81. In the same way, let's think about this. This means the base is x. This is the power, or the exponent, because a log equals the exponent, right, is 125. So this question is saying something cubed equals 125. And so that, of course, would mean x is 5. Interpret what this next one means. Now I'd like you to actually solve for x, and I'm going to look for that answer as part of your notes this time. I want to see that you actually have solved for x. Don't just write it all down, but actually come up with what does x equal for log base 10 of x equals 3.